polynomial characteristics, and we're going to graph some polynomials today. That's kind of actually what we're working towards, is graphing polynomials. Okay, so polynomials, those are basically those graphs that look like this, or they can look like this. So I'll tell you guys some characteristics, and then I'll write them down for you so you can copy them down. But they're infinite functions. They go on forever. They always approach positive or negative infinity. They're always continuous, so it's a smooth curve here that with no breaks or gaps. They are curved, so there's no sharp points or anything else like that. When we write equations for these, they have groups of terms with exponents that are always whole numbers. So we're not going to see any like square root of x or x to the 3/2 power or anything like that. It's always going to be x to the 0, 1, 2, 3, 4, etc. No negative exponents either. And yeah, I think that's all the main characteristics. Did I say them all? Yes, I did. And there's some other stuff that we'll know based on how the equations are written. So polynomials, let's write that down. Okay, so I did forget to mention one thing, is the coefficients are always going to be real numbers. So notice here the exponents for our variable x are all whole numbers. X to the 0 to the first power, 2, 3, 4. But the coefficients, the number out in front, they can be any number as long as it's not imaginary. So any real number is fair game. This one here is in standard form, which means it's written with separate terms here, 1, 2, 3, 4, 5 terms, separated by addition or subtraction. And the terms are written so that the exponents are in descending order. So the biggest one is over here, smallest exponent over here. So this is the constant term on the end. This one we call the leading term. 3x to the 4th is the leading term because it's the one with the highest exponent. Do you guys remember the name for the highest exponent? What we call it? The blank of the polynomial. The degree of the polynomial. So this is 4th degree. So I'll write that down. So one thing too about the constant term, the one with no variable at the very end, that will tell us the y-intercept as long as it's in standard form. A couple other things we can learn from the degree of the polynomial is this polynomial will have exactly 4 roots. They might, because it matches the degree. Some of them might be imaginary, and some of them might be repeated, like it's a double root, but there will be exactly 4 roots. And there will be at most 3 turning points, which is 1 less than the degree. So this little sketch here is a 4th degree polynomial. It's not the one that matches the equation, but we can see it has 4 roots. It has basically 2 real roots and 2 imaginary roots. They wouldn't really be there, but because they're imaginary, but that's the imaginary roots would be represented by that part of the graph. And then we can see it has 3 turning points. And we will call those maxes or mins, maximums or minimums, or extrema. But for right now, we can call them turning points. Okay. So that's polynomial in standard form. We're going to look next at a polynomial that's not in standard form and talk about some other things that are going on with this one. That's a 4. Turn to your neighbor. Do you know the name of the form that this is in? Anybody know it? Anyone know what these things are called? They are parentheses. The things in the parentheses are like the whole group of it together. Factors, yes. So this is factored form. Nice. Factored form is easier to graph. It's much easier to graph. We prefer to use factored form. Just in general, it's more helpful. Our goal is usually going to be to get polynomials into factored form if they're not in factored form. Turn to your neighbor. What is the degree of this polynomial and what is the y-intercept? Okay. Who knows what the degree is or thinks they know? Liv. It's not 3. Good guess. Sabrina. Huh?
1.
It's not 1. Mark. It's 6. Yes. How'd you get that? The exponents. Yes. Yes. So if we add the exponents together, that will tell us the degree when it's in factored form. Okay. Now that's how you add. That's how you find the degree. That's not why the degree is 6. So imagine, you don't need to do this, but imagine if I were going to multiply this whole thing out. So you don't need to write this, and you don't need to multiply it out. Let's just go ahead and say don't multiply it out. But if you were to multiply it out, you would get, like if I multiplied this first one out, x cubed minus 1, I think, would be, don't quote me on this, no, minus 1. I think it would be plus 3x minus 1. That could be right. I could be wrong. Don't quote me on that. It would be something like that, times x plus 2, x plus 4 squared if you multiplied it out. You can quote me on this one. This is x squared plus 8x plus 16. Imagine if I were going to keep multiplying out here. I would have to, multiply x into this and the 2 into that. And then whatever results from that, I have to distribute into there. Okay, so this would get kind of crazy, right? But let's just think about what the leading term would be. If I just was going to do part of this, if I did x cubed times x, what does that equal? So x cubed times x equals x to the 4th. And then if I took that x to the 4th and I multiplied it here to this x squared, we would get x to the 6th. So, not squared, hello. So x to the 6th would be our leading term. And so that tells us that the degree is 6. Now, the short way to do that is you just add these exponents. X cubed times x squared is x to the 6th. That's where we get it from. But this is why that happens. You will never need to multiply something out from factored form, so don't do it. If you're doing it, it's because you love to multiply, not because I asked you to. If you love to multiply, that's okay. What's the y-intercept? Well, you are correct. How'd you get that?
Well, the y-intercept is the x would be 0. Y-intercept. Plug in 0.
That is correct. If we plug in 0 for x, let me just erase some of this here. It's a little chaotic. If we plug in 0 for x, that will tell us the y-intercept. So this would become right here -1 cubed, because it's 0 minus 1. So -1 cubed times 2 times 4 squared when we plug in 0 for x. So -1 times 2 times 16 is -32. And that's how we get the y-intercept. So in factored form, it is easier to graph. We like using it more. It's just a little bit more work to find the degree in the y-intercept. But it's a lot less work to find the zeros or the x-intercepts. Turn to your neighbor. What are the zeros of this polynomial? Okay, what are the zeros? Do we agree? Yes. Okay. So, to get those, how did you get those?
I looked at the factors from the original problem, and if you just make them like an x equals problem, you have x by itself on one side with all the numbers on the other. So
Yes.
basically for x minus 1, it would be x equals 1.
Yes. Yes. So one way to describe that is set factors equal to 0, but what you're saying is like x minus 1 equals 0. We would have to add 1 to both sides, and we get x equals 1 as our 0. Yeah, that's exactly right. So whatever makes each one of those factors equal to 0, those are the zeros of the graph, the x-intercepts. Now, in this problem right here, we have what's called a multiplicity of factors. Everybody say multiplicity. That's a word, if you throw it around, you sound smart. We have this factor is repeated 3 times. And we have this factor is repeated twice. So we do have 6 total zeros to match the degree. We have -1, -1, and -1. We have, sorry, 1, 1, and 1. 2, -4, -4. That's a total of 6. But we would say this is only 3 distinct zeros. So, based on the multiplicity, some different things are going to happen. So when a factor has an odd multiplicity, it's to the 3rd power, 5th power, 7th power, etc. We have a point of inflection. At that 0. Or the graph passes through the 0 with an inflection point. Who remembers what happens with even multiplicity? X rebounds. Yes, it's going to rebound or bounce, or it can be called a point of tangency. Yes. So if there's no multiplicity, it's just to the 1st power. The graph's just going to go straight through. Okay, we have almost everything that we need in order to graph this polynomial. The last thing that we need to talk about is end behavior. So what end behavior refers to is describing f of x, the function, as x approaches positive infinity and negative infinity, or the far right of the graph and the far left of the graph. And behavior is determined by two things in a polynomial, I should say. Turn to your neighbor, what are those two things? What determines the end behavior of a polynomial? I'll give you a little bit of a reminder here. We have 4 possibilities. We're going to fill out a chart in just a second. So it could, the end behavior could look like this, or this, or it could be like this, or this. So again, we're talking about what's happening at the end. So both ends of the polynomial are going up, both ends are going down. One up, one down, or vice versa. Those are our possibilities. So what determines? What are the two things that determine what it does? Sabrina. Okay, if what's positive or negative? The leading coefficient. Yes. Very nice. What's the other thing? Will?
The degree, right?
Yes. What about the degree?
Whether it's like even or
Yes. Very nice. So, when both ends of the polynomial, so the left column here, are doing the same thing, either both up or both down, what is that telling me? That is even degree, yes. So these would be odd degree. For even, if both ends are up, then what's true about the leading coefficient? It's positive. And for odd degree, that means it starts down and goes up. For odd degree, I like to remember that the x values match the y values when it's positive. So positive x's, positive y's. This would be negative leading coefficient. And so because we're talking about polynomials, we're talking about this specific family of functions. The functions themselves, the y-coordinates, are always going to be approaching positive or negative infinity as x goes to positive and negative infinity. We have 4 possibilities, but it's always going to be infinity. This is not true of every function. Some functions approach a horizontal asymptote. Some functions don't even make it to infinity at all. They don't even exist past a certain point. Some functions are waves. We're going to learn about sine waves this year that just go back and forth forever and never approach infinity or even a specific number. So in the polynomial family, we're always going to one of the infinities as we get out there. Okay. Now we are ready to graph that polynomial that we were looking at. So I'm going to rewrite it here so I can see it. So we have our degree is 6. That's even. The leading coefficient, do you guys remember if that was positive or negative? It was positive, yeah. So when we multiplied everything out, basically there's no negative sign in here. So this is going to give me positive x cubed times x times positive x squared. It's just going to be positive x to the 6th out in front. So that's going to give us this kind of end behavior, both positive. The zeros, we talked about those. They're 1, -2, and -4. And I'm just going to go ahead and label those as well. We have our y-intercept here is -32. My graph's not to scale. That's okay. Make sure you label your graphs. So then I can start graphing here. I know my graph is basically going to be doing that. It's pointing up on either end. So as my graph approaches -4, what's going to happen when it gets to -4? Is it going to go through, is it going to bounce, or is it going to have an inflection point? It's going to bounce, yeah, because we have an even multiplicity there. It's going to bounce. It does need to turn back around to go through -2. So it's not going to bounce up forever. It needs to just turn around, go through -2. How's it going to pass through -2? Yeah, it's just going to go straight through. Boom. The next point that we need to hit is that y-intercept, -32. We don't know exactly how the graph is going to behave. I'm just going to have it come down here and then turn around and hit -32 on the way up. You could have it hit -32 on the way down. I think it'll just fit easier if I do it this way. And then it'll come up towards 1, and then how's it going to interact with that 0? Straight through? Inflection point. It's going to have an inflection point. So the way that you draw that is you're heading up towards 1, aim a little bit to the left of 1, have it flatten out a little bit, and then continue on up. So there is a moment there where the slope is 0, like it's flat, but just a moment, and then it keeps going up. And so there's your graph. Any questions on coming up with this graph here? All right, so now you guys are going to get to put it together. I'll just put number 3 right here. Okay, go ahead and graph this one. Ooh, So as you're doing this, make sure you're thinking about the degree, the leading coefficient, whether it's positive or negative, the end behavior, the y-intercept, and the zeros. And you can talk about this with your partner as well. So there's just a reminder of what you need to do for each one. All right, let's check. What's the degree? 5. We add those exponents, 2 and 3. Leading coefficient, positive or negative? Positive, yeah. So basically we don't see any negative signs here. Like if this was negative x minus 4, the leading coefficient would be negative. Because when we multiply that out, we would get negative x cubed. If this was negative x plus 3, the leading coefficient would still be positive because that would just give me a positive x squared because I'm squaring a negative number. That's basically what we'd be looking for. Is there a negative and is it in an odd factor? But basically just imagine what would happen if you did multiply it out. So what's our end behavior look like? Show me with your hands. Yes, very good. Like that. Okay. What is the y-intercept?
Negative 576.
Negative 576 is correct. So we need to plug in 0 for x. It's 3 squared times negative 4 cubed. So it's negative 64 times 9. So you might just have to multiply this the old-fashioned way. 4 times 9 is 36. Carry the 3. 9 times 6 is 54, plus 3 is 57. Negative 576. So we'll just put it down there. And what are the zeros? Nice. Okay, I'm going to introduce you guys to some new notation here, maybe. It might not be new, actually. I'm going to write negative 3m2, which stands for multiplicity 2, because it's repeated twice. And 4m3. So go ahead and get used to writing this in here because we just want to make sure that we're keeping track of all the zeros. There are 5 zeros, but there's just 2 distinct zeros. So negative 3 and 4. With multiplicity 2, what happens at negative 3? Bounce. Yeah. Boom. Go down here to 576. Again, we don't really know like which side it's going to cross on. Maybe it goes like this. We don't know. That's more of a calculus topic, is knowing where the turning point is. And then as it goes through 4, what's it going to do? Inflection point. So I'm just aiming a little bit to the left here, flattening out, and then going up from there. There you go. Questions on this graph right here? Okay, I'm going to show you guys some new notation for the end behavior. Back in Algebra 2, you probably would have written something like this: as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. We are not going to use that anymore. We are going to use what's called limit notation. It's going to say the same thing, but we're writing it differently. So it's going to look like this. the limit of f of x as x approaches infinity equals infinity, and the limit of f of x as x approaches negative infinity equals, whoa, equals negative infinity. Oh my gosh. And I wrote that down there just so that you know how to say that. We'll talk more about limits this year, but that's basically how we're going to write end behavior. It's the same thing. We still have the x going to infinity, and the y going to infinity is just the equals infinity part. Okay, so yeah, let's do some more practice with graphing. Go ahead and graph this one. Same process as before. And you guys can work together on this. So I want to think about degree, leading coefficient. We did this one. That's the same one. This one, here it is. We did that one. This one. This one. Okay, so something we want to notice about this one is that it's not in factored form, it is in standard form. But you probably can factor that one pretty easily, hopefully you can. But we're going to notice some different things about it right away. Because it's in standard. Okay, let's talk about this one. So this one is in standard form. It's not in factored form. Standard form means that we can see the degree and the y-intercept and the leading term from the very beginning. So what is the degree of this polynomial? Yes, some of you guys are doing this. It is 3. Okay, so here's our leading term. Our degree is 3. So we don't add the exponents here because notice like they're not being multiplied. It's x cubed minus 2x squared. And that's how we can tell the difference between factored form and standard form. So that's the leading term right there. What is the leading coefficient? Is it positive or negative? Positive. And it's the number what? 1. Yeah, it's positive 1. We can see it right there. Positive is what we care about for the end behavior. So what would that look like? Can you show me with your hands? Yes. Like that. We can also see the y-intercept from standard form. It's the constant term, which is going to be on the end, which is 0. Yeah. So it's like we have a little plus 0 in the end there. That also means that one of the zeros, or the x-intercepts, is 0. What would we need to do to find the other 0 or zeros? Factor, yeah. And how would we factor this? Yeah. Take that x squared out, so it's x minus 2. So it's not, one of our zeros isn't just 0. What else would we write? 2 is the other 0, but what would we write by 0? M2 for multiplicity 2. So what's the graph going to do when it hits that x-intercept? Bounce. It's going to bounce. Yep. So it starts here, bounces, comes back through. Like that. Let's go ahead and add here for our end behavior. The limit of f of x as x approaches infinity is infinity. And the limit of f of x as x approaches negative infinity is negative infinity. Once you've got that one, you can go ahead and move on to number 5 at the bottom there. And that'll be our last example for today. So I'll take a little more time on this one, but just notice it is in standard form, just like the last one. So we can figure out a lot of what we need to figure out right from the beginning, but we will need to factor this in order to get the zeros. It'll take like 30 more seconds to get that. All right. What's the degree? 3. What's the leading coefficient? Positive. Yeah, it's positive 2. There it is right there. There's the degree. Okay. So that means end behavior. Show me. Yeah, same as the last one. Very nice. Y-intercept? 0. Yeah, this also is missing a constant term, so that's 0. That means one of our zeros is also 0. When we're factoring this, to find the other zeros, what should we do first? Yeah. We got a GCF. Okay, so then this is, we still need to keep factoring the inside there. This is one of those where it has a, leading coefficient of 2. I mean, we already knew that was a leading coefficient, but we need numbers that multiply to what and add to what? Yeah, -8 and -7, what are those two numbers? -8 and 1. So 2x squared minus 8x plus 1x minus 4. GCF of the first group? 2x. GCF of the second group? Yeah, there's none. So I like to just write 1 to remind myself how that's going to work when I do the next step. This means my factors are going to be 2x plus 1 and x minus 4. And then factored fully, we still have the x out front. So don't forget the x out front. So what are the zeros? Positive 4 I agree with. Negative 1/2. Negative 1/2. Because we want to do 2x plus 1 equals 0. So minus 1, then divide by 2. Okay, so We have it like here, negative 1/2 and 4. We've got our end behavior. Any multiplicity with our factors? Nope. So we're just gonna boom, boom, boom. There we go. Any questions? All right.